In this year's lectures, we introduce some basic and important concepts in calculus. As an entry-level course, we often adopt approaches that are intuitively clear but might not be mathematical rigorous. In particular, we will not use the famous epsilon delta language. In this lecture, we'll introduce the Riemann integral and some of its basic properties. First of all, let's try to understand the idea behind the Riemann integral from the geometric perspective. All right, so basically what we want is we want to compute the area. Okay, here's the setup. Suppose we have a graph, we have a function which is positive. So here's the graph or function. All right, the function is defined on the interval a and b. This b and this x. So the graph is y equals fx. This is the y-axis, and here's the 0. Now we look at the region that is below the graph, but above the x-axis. And what we want to do is we want to find the area of this region. In plane geometry, we know how to calculate the area of a polygon and also the area of a circle. But sometimes if you have irregular shape, if we are able to divide irregular shape into a combination of regular shapes, then we can use the cut and paste method to find the area. So here, for a general function f, x, this region, which is not of those regular shape, is curved. So how should we find this area? We are going to use the idea that's kind of similar to the cut and paste, but in general, you cannot exactly cut into regular shapes. So what we do is we do a kind of approximation. No, it's not exact, but we use approximation. So approximate it by rectangles. Right. Okay, so basically we say we cut it, right? All right. Okay, so how we do it? What we do is we say, okay, we divide, right? So AB into small pieces. You can use equal distance, or you can use whatever partition you want. All right, so let's say then we can divide the region not exactly into a union of rectangles, but approximately, right? Okay, let's see it. So that's what we have. Okay, so we have this rectangle, and then we have this rectangle, and then we have this, and then we have this, right? Okay, so we have this, you just draw all of them out. Okay, so that's what we have, right? Now, so the idea is, if we look at the area, we say, okay, let's look at the area, total area of all those rectangles. Right? We look at the total area of these rectangles. And we expect, okay, they're not exactly the same as the area below the graph, but we expect that this total area and the area of the region we are looking for, they are not exactly the same, but it's kind of approximately, right? It's close. It's close to it. Okay, all right. Let's try to express the total area of those rectangles. So in order to do that, we introduce those letters. So the x0 is a. So the first one is x1, and this is x2. This is x3. This is 4, and such, right? So okay, let's say this is the xn minus 1, and the b is xn. Okay, so we just divide it into n pieces. Of the interval AB is divided into n pieces, right? Now let's try to express the area. Let's look at the area of the first one. Here is the width, right? So then this is the length. So that's how we calculate the area of rectangle. Is the width multiplied by the length, or we say the width multiplied by the height. What's the height? Okay, it's just a value of, it's just FA, right? So the height, this is just the value of the y coordinate is FA. So this one is FA. So the area of the first one is just height FA. All right, so look at the areas FA multiplied by the weight. Well, weight is right here, which is x1 minus a. And the other similar. So it's okay, how about the second one? Again, if you try to find the area, it will just be f times x1 and times x2 minus x1. and such, right? And let's look at the last one. So last one, we say, okay, so what is the height here? The height, so that this height will be the y coordinate, will just be fxn minus 1. And then the weight will just be xn minus 1, right? Xn, which is b. Okay, now you sum them up. So let's sum them up. Sum up. Okay, so we just get the summation, the total area equals, let's say this k, let's say it's I, so it just be I, right? From 1 and to n, so this f, right? So this is the height, this is x times I, and here will be xi minus 1. So this is xi minus 1, right? Okay, and multiply by the weight, which is the xi minus xi minus 1. All right, so we just sum them up, right? Okay, this is the area of those rectangles, and we expect this one will be close, right? We say, okay, well, this one will kind of be close to the area below the graph y equals to fx. Now, again, they are not exactly the same. So how should we make them to be the same, right? How can we make them to be the same? And then you see, if I make this one, so this is the length, right? So that the width of the those rectangles. So if I make this xi minus x1, so those things, right? So those things, if you look at it here, if I make this to be 0, as small as, not exactly 0, but if I make this go to 0, make it very small, right? Make it very small, then we'll expect, right? Intuitively, so okay, that means I just make the division finer and finer. Then you expect this will eventually converge, right? Will converge. Okay, so this is going to be converged to the area below the graph. Now, one example can demonstrate this is you can look at a circle, right? You say, okay, how can we compute the area of the circle? Well, suppose you don't know the formula. So what do? Is okay, you use square to approximate, but then of course this is not very accurate. Then you say, okay, then I use hexagon, right? Regular hexagon to approximate, right? Still, but this is closer, but still not exactly the same. And then what you do, of course, you just divide small, like more and more pieces, right, of this circle, and you just calculate the area of this polygon. And then you see, like if the side, like if the number, let's say this is n polygon, right? If you use n polygon to approximate the circle, if you let the number of edges go to infinity, then of course you expect the area of the polygon will converge, will get closer and closer to the area of the circle. So that's the basic idea, right? So we get this kind of sum, and then we want the step size to go 0. We expect this will converge to this area, right? To the area below the graph. And the area below the graph, so this is what we are going to write. So it's okay. So this is something we are going to write as the integration from a to b, and the integral of a to b fx and dx. Okay. Now, so this is how we understand the integral from the geometric perspective. Now let's look at it, one of its most important application in physics. Okay, so here's a setup. Suppose that you have a particle that's moving along the x-axis, and the particle starts from here. So this is starting point. Let's say t equal to 0, right? And it's moving, say for example, like moving to this direction. Vt represents the velocity. That means the velocity is not constant. It changes according to time. So what we call is instantaneous velocity, right? At the moment t. All right, so now we fix 2 moments, say from A to B, and we want, let's say B here. Okay, so we want to find, okay, what is the travel distance from moment A and to moment B? The usual formula in high school, you know how to calculate the travel distance. We say, okay, the travel distance equals speed multiplied by the time. So here time, is just B minus A. However, here, the trouble is the speed is not a constant, right? It's instantaneous speed, it's not a constant. All right, so we cannot just use the speed multiplied by time. Then how should we do it? The idea is similar to the previous one, but just from a different perspective. What we do is, okay, again, what we are going to do is we are going to divide, let's say we divide the time into small pieces, right? Okay. Say this is will be a T0, this will be T1, this will be T2, this will be T3. Let's say this is Tn, and this is Tn minus 1, right? Okay, now we look at, suppose, let's say this is Ti minus 1, and this is Ti. And let's say we try to find the distance. And we look at, we say, all right, let's look at the travel distance between the time Ti minus 1 and the Ti. Okay? Because this Ti, because Ti minus 1 is very close to Ti, very close, then we can think of, approximately think of, we can think the speed is constant. So it's okay, approximately we can think the velocity within this is, we say, okay, it's the same thing as the Ti minus 1 within this range. Approximately, we say, okay, it's just the same thing. All right, and then the travel distance between that will just be Vti minus 1, right? So this is speed, approximately, again, it's approximately, keep that in mind, and multiply by the time, so that Ti minus Ti, right? Okay, so it's time, which is Ti minus 1. And this approximately represents the travel distance between Ti minus 1 to Ti. Then you say, okay, from here, how can we get approximate of travel distance from A to B? You just sum them up, right? It's okay, now I sum them up. You say, okay, so let's just sum up. Let's sum up. Then I get a total summation, I from 0 to n, right? From 0 to n, and this Vti and Ti minus 1, right? So this will be approximately, right? Approximately, the travel distance. What we are looking for? Travel distance between time A and time B. Now they are not exactly the same, but how can we make them same? Similar. We say, all right. So if I let this time interval, right, get small and smaller, get smaller and smaller. So if I let the Ti minus 1, this one goes down to 0. I let it go down to 0. Then we expect this summation, right? So that means we divide the partition, right? Just means the partition gets finer and finer, right? Partition gets finer and finer. We expect this sum will converge to the travel distance. For this one, again, we express this as the integration from A to B, and this is the fx and the dx. All right, so you see the essential idea is similar. What we do is we say, okay, because in the geometric perspective, because the region is not regular, so we try to approximate it by rectangles, right? But this, again, if you write down the area of the sum of these rectangles, as we said, this is only approximation. It's not exactly the same. It's approximation. But what we can do is, if we let the partition get finer and finer, we expect that this one will converge to the real area below the graph, right? And that's we write. This is how we denote the integral. And here the travel distance is similar. Because the velocity is not constant, we cannot just use the velocity to multiply time. We have to divide the time interval into small sub-intervals. The idea is within each small interval, right? Within each small interval, we can say within this small interval, the speed, the velocity is approximately constant. Then we can say, okay, approximately, we can compute the travel distance within this small time interval from ti to ti minus 1. And then what you do is you say, okay, I sum them up, right? Within each small time, I sum them up, and I expect that this will be approximation of the real travel distance between A and B. Now, mathematically, you say, okay, and intuitively it's clear. If I let a time interval to go down to 0, we expect this will converge to the real travel distance, right? To the real travel distance. Okay. All right. So based on these two, and here we can have the real definition of Riemann sum and Riemann integral. Okay. All right. So here's the setup. Suppose, right? So we have interval. This is from A and to B, and we divide this into small sub-intervals, not necessarily of the same equal length. So they don't have to be have the same length, right? Okay. All right. So we say, all right, we just divide into small intervals, and this is x0, right? So this is x1, this is x2, x3, x4, and this is xn minus 1, right? And this is the xn. Okay. All right. Now, well, and then we introduce, we say, okay, within each interval for here, we choose a sample point. It just means you can choose any point that is between, right, any point that is between the A and X, and then here you can choose a sample point, right? So in general, we say, okay, here I choose this is xi minus 1, and this is xi. Right, you can choose the sample point. This is xi star, right? Choose sample point. Now you evaluate f on those sample points, and you sum them up. And this is called a Riemann sum. So Riemann sum, of course, it depends on that how we divide the interval, right? You say, okay, you divide the interval into two pieces. And so you divide the interval into 4 pieces, or you say, okay, I divide into 5 pieces. And of course, it depends on how you choose the sample points. So I can choose sample point from here. I choose the left end point. I choose the middle point of each interval. I choose here, whatever you like, right? So you have different ways to divide the interval. So those are, we call it partition. And then you have different way to choose those sample points. Doesn't matter. As long as you decide a partition and you choose those sample points, then you get a Riemann sum, right? Get a Riemann sum. Okay. And the idea is, as we said before, now if I look at this is the maximum distance between those sub-intervals, right? The maximum distance between those sub-intervals. Now I want this to go down to 0, right? So okay, so basically we're looking at I look at the partition to get the finer and finer, right? And I expect the limit of those Riemann sum, right? This Riemann sum to converge to what I want. For example, the area in geometry or the travel distance in physics. Now the question is, mathematically, regularly speaking, can we guarantee the limit will exist? Okay, so does the limit exist, right? Can you guarantee mathematically, can you guarantee the limit exists? Well, that's not completely obvious, but we say, okay, so suppose we have this Riemann sum, right? Riemann sum, and we say a function, this is definite, we say function is Riemann integrable if the limit exists. So here limit exists just means those step size will go to 0, right? Step size will go to 0. Of course, then of course the number of intervals will just go to infinite, right? Okay, so the step size will go to 0. Now, if the limit exists and is independent of how you choose to divide the interval and how you select those sample points, regardless how you do it, right? How you divide the interval, as long as you make the partition gets finer and finer, right? So if you make the partition gets finer and finer, then the limit exists. Okay, so if that is the case, we say it's integrable, and this is how we represent the Riemann integral. Now here the point is the limit of the Riemann sum exists, and it doesn't matter how you divide the interval, how you choose those, As long as the step size goes down to 0, the limit is the same. It's the same limit. Okay. And then you may be asking, how do you know this is going to happen? Well, the good news is, yeah, we have some theory to guarantee if the function is continuous, right? So if you have a continuous function, okay, so if you have a continuous function, right, or you have, say, piecewise continuous, that means you allow, say, okay, there's jump discontinuity, which is fine. You allow have several discontinuous. Doesn't matter. But as long as the function is continuous or it's piecewise continuous, then it's Riemann integrable. That means we are able to guarantee the limit exists, and it's independent of how you divide the interval and how you select those sample points. Okay. All right. Let's look at the geometric meaning of Riemann integral to find the following things. Let's look at the first one. Here, we want to find the Riemann integral of x and dx. As we said, this is a continuous function, right? We know this one exists. Okay. The geometrical meaning means it's the area. So this one equals the area of, let's draw the graph, right? Okay, let's look at the graph. This is the x, this is y, and this is 0. Okay, so it's from 0 to 1. So the graph is y equals to x, right? This is y equals to x. And it is the area of this region equals the area of the region that's below the graph and above the x-axis. And we say, okay, this is a triangle, and we know to calculate the area. The area just equals to 1/2 times the height times the two sides, two legs. Right? Okay, it's 1/2. So we get is 1/2. Let's look at the second one. Here, let's look at this. So let's look at the graph of the function, right? So what do we have? Okay, so here my graph is when it's between this is -1 and let's see. Okay, let me redraw it. Here we have here. Okay, let's draw the graph. So here what we have, right? Okay, so let's draw the graph. 0, the origin x and y. When x is between -1 and 1. This is 1 and this is 2, right? Okay. The graph, it's when it's from -1 to 0, it's 1. It does not include point 0, which is right here. And between 0 and 1 is 2. Okay, so this is 2. And this is my function, y equal to fx, and it's discontinuous, right? It says discontinuity at the point 0. But doesn't matter, as we said, it's piecewise continuous. The function is Riemann integrable. All right, so all we need to do is we say, okay, it's just area. It's okay, it's just the area, right? It's the area of the region. Region, so it's area of this one. Well, both of them are just rectangular, right? So the area of this we know equals 1, and the area of this equals 2. So you just add them together. So area will be 1 plus 2, which equals 3, right? Okay. All right, now let's look at example 2. Again, we want to use the geometric meaning of Riemann integral. Okay, so Riemann integral, not integration. So Riemann integral to find this one. So from 0 to 1, the square root of 1 minus x squared. Again, let's draw the graph. We say, okay, so we know this is just the area below the graph, and the graph is y equals the square root of 1 minus x squared. So this is x, and this is y, and this is 0, right? Okay, all right. What is it? First of all, let's try to identify what kind of graph is this. So y equals this. This is non-negative. Y squared, I take the square on both sides, and we get x squared equals y squared equals 1. Oh, we know this is just the circle of radius 1, right? So this is -1 and it's 1. Okay, so it's just like this. So that's what it is. And y, it's the up half, because by this formulation, y is not negative. So this is y equal to the square root of 1x. Okay, and then what do we have? It's just the areas. Okay, just the area of this, right? So this one just equals the area. Right? And we know how to calculate the area of a semicircle, it's just half of, right? So this one just equals 1/2 times pi times the square of the radius, which is 1. So we get this one is pi over 2. Next, let's look at some basic properties of Riemann integrals. Okay, not integrals. Let's look at Riemann integrals. Okay, so here is let's look at this. Let's look at the first property. The first property basically says the Riemann integral is linear. You can the sum of integral of the sum equals the sum of integrals. Let's see. Let's try to understand like why this is correct. Because we know this one is given by Riemann sum, right? If you remember, we say okay, all those things can be understand easily from the definition. It's given by Riemann sum. You know, okay, so this is just the limit of Riemann sum, right? You know, sum up. This is the f. If we use the sample points, right, plus sample points plus t, also evaluate those sample points and times the length of interval, right? So this is just how we calculate the integral by definition. And then of course you can just split this into two, right? This is fxi times xi minus 1 and plus the summation and g xi star times xi minus 1, right? And then you notice this one will just approximate to that, and this will just approximate to g. Okay, so my point is, if we go back to the definition of Riemann integral using approximation, right? Using approximation of the Riemann sum, then we can quickly establish the property, the sum of the integral of the sum equal the sum of integrals. And similarly, you can also do this, right? The integral of difference equals the difference of integrals. And this one is also similar. You say, okay, if I use the Riemann sum again, you just go back to the Riemann sum, right? Recall the definition, remind yourself of the definition. So, okay, you know, this is just given by the Riemann sum, right? So, okay, sum them up. This is lambda. This is fxi star with the sample point. Then you fi minus xi, you sum them up. But then for this one, you see, you can pull the lambda to the front, right? And it's okay. So this is lambda times, this is fxi star times xi minus 1. Now you see, what's this? This one will just approximate to that. And the lambda's here. Of course, this will just approximate to the whole thing, the lambda one. Okay, again, you see it's obvious why those properties are true if we look at the original definition using the Riemann sum. Now we can use those properties to calculate integrals. Let's look at the first one. So this, if I want to calculate 2x plus 1, well, we can use two methods, right? So say method 1, let's use the geometric definition. We say, okay, we use the geometric definition. We know, well, the geometrical meaning, we say, okay, A just the area below the graph. So this is X and this is Y. So we look at the curve, right? Look at the curve. This is just a line, right? So this is a line. Okay, from 0 to 1, when X 0, Y is 1, and this will be 3, right? So okay, and this will be 3, right? 3. All right, so now what we are looking for is the area of this region, right? So we are at the area of this region. This is trapezoid. Yes, 1. This is trapezoid. And we know the areas. Okay, so this just equal the area. The area equals, if the trapezoid, you can see it's 1 plus 3, right? Multiplied by the height. So here the height is also 1. And divided by 2, right? So 1 plus 3 and divided by times the height divided by 2, right? So okay, so this is, we get as 2. So this is method 1. Method 2, you can actually use properties, right? So okay, we say, all right, let's use the property method 2. Use those properties to simplify the calculation. You say, all right, so if I want to calculate 0 from 2x plus 1 and dx, I can separate this from 0 to 1, 2x dx, right? And then plus this from 0 to 1 and 1 d1 dx. And this we know is constant function is just 1, right? And here you say, okay, so the 2 can move to the front, and this one just equals the 2 integration from x and dx. And this one we did it before. We know this one is 1/2. Okay, so we get is 2 times 1/2, right? So okay, it's 2 times 1/2, which equals 1. All right, so what you have, you just get is the final answer will just be this part is 1, this part is also 1, so it's 1 plus 1 is 2. Get the same answer. All right, so my point is, in many cases, you can use the property to simplify the calculation. Now, let's look at the second one. We do, okay, so for this one, we'll just use the geometric way to do it. All right. Okay, here is the differences between -1, right? So between -1, so this is -1 and -1/2. Then it's 0. Whereas -1 is -1, right? This is also -1. It's here. So this is the graph. And okay, so this is the graph. But now here you should be careful because this is negative, right? So here is negative. What to calculate is the integration over here. Okay, so it's negative areas. Okay, what we get is negative area. Another way to understand this, if you flip it, right? So if you flip it, if you look at negative 2x plus 1, then you get a positive, but you have a negative sign, so you should to the front. Okay, you get the negative area, so which is it's negative, right? So put a negative sign. The area will just be 1/2 multiplied by this is 1/2. And this is 1, so 1/2 times 1 times, we get the answer, this will be -1/4. So here's the negative sign, and the final answer, we put it here, and the final answer will be -1/4, -1/4. Now let's look at other properties of the function of the Riemann integral. This is a comparison. If I know one function fx is no less than another function gx, then the integral is also no less. It keeps the same order. Well, this is kind of clear, right? So, okay, so again, everything, if you try to understand those properties, let's just go back to the Riemann sum. We know this one is approximated by the Riemann sum, the summation that f evaluated at a sample point, and you multiply by the step size, right? And this one is approximated by g evaluated at a sample points and times xi minus 1. Now, trying to understand why those properties are true helps us to review and recall the original definition of Riemann integrals. And then you see, because this one and this one is big or equivalent, right? So this is no less than that. So it's okay. So obviously, the Riemann sum of f is no less than the Riemann sum of g, right? If we use the same partition, same sample points, and this one convert to this, and this one convert to that, right? Okay, so then of course it will keep the same order. And this will be similar because if you let 0, right? So we know if you change this one to be 0 dx, this of course just 0, right? So if this one is greater than 0, you just get this positive. If less than 0, you just get this negative. And that's similar to the problem we studied before, right? If you look at this problem, you just get negative, just like here, right? So if you look at this example, here we have a negative, right? So if you look at this function is negative, so the integration, you get basically just negative area, right? So this is, for this one, you say, okay, if I have the graph of f is like this, right? And then you do the integration, so this is less than 0. You do the integration, so the integration will just be the negative. So what you get is the negative area. So this, okay, so the area you get is the negative area, put the negative sign in front of it. All right, we can look at other properties of this integral. So, okay, so if you do, you say, all right, this is from a geometric point of view, it's very clear, right? You say, okay, if I look at the graph, right, so this is from A to B, this is the area, right? So this is the area, okay, so this is total area, right? Now, if you choose a point between here and you say, okay, this is the area 1 will be this one from A to C. And then you have area 2. We say, okay, so this is the area 2, right? So, okay, so then it's this part. Of course, it's the sum, right? All right, here is a definition. Here's a definition. If you switch the order, then you just put negative signs. For example, from 0 to 1 fx, you say, hey, what if I write things like 1, 0 fx dx? And then by definition, here we just put this is, if you switch the numbers in the integral, and then you put a negative sign, okay? You put a negative sign if you switch it, if you reverse the order of integration, and then you put a negative sign. Well, of course, like if you just from A to A, there's nothing, and just 0, right? There's no area. All right. Now let's look at past the problem from AP calculus, AP exam. Okay, so here what we have, let's look at here. It's -10, right? And then we have 4, and then we have 6. It first says the integration from 4 to -10. Well, but you see, first of all, you look at it here. 4 to -10, gx dx equals -3. And you see, this is not in the regular position because 4 is greater than -10. So you have to switch it, right? So from here, you switch it. You get it from -10, you switch, reverse it. So gx dx will equals to -3. So it's 3, right? You switch the order, and then you put a negative sign. So you get this one 3. And then you have from 4 to 6, right? So, okay, from 4 to 6, gx dx equals 5. Now then the total, right? So the total integration from here to here is 3. From here to here is 5. And we say, okay, so then from total from 10 to 6, gx, you know, this is a summation from plus to 4, gx dx, right? And then plus from 4 to 6 and gx dx. Okay, so you just add them up, right? This equals to 3. This equals to 5, right? Equals 5. You just add them up. So the final answer will be 8. Example 5. This is again is a past the problem from AP calculus. Here we have the graph of the function. The graph of the piecewise function is given by this, and we want to find the integration from -1 to 4. When we look at this graph, you see one part, this is positive, right? And then you have another part, which is negative. All right, so let's do this separately. Okay, so first we say, okay, we can do the integration. So first of all, we say, all right, so if I do the integration from -4 and this fx dx, I first do the part, which is okay, which is from -1 to 2 fx dx. Then I do the part from 2 to 4 fx dx, right? Now, for this part, we say, okay, it's just the area, because it's positive, it's just the regular area. And this is trapezoid, right? So we can use, this is the top side, right? So the top side, this is 1. So it'll be 1 plus the bottom, which is 3, multiplied by the height, divided by 2. So this is 4. Okay, so the area of this one is 4. Now let's do this part. This part, as we said, this is negative. So this is negative area. It's a negative area, right? So it's negative. Again, it's trapezoid. This is 1, this is 1, and this is 2. Okay, so it's 1 plus 2. The top plus bottom multiplied by the height, divided by 2. Okay, so you get this negative. So this part is negative. It's negative 1.5. Right? It's negative 1.5. Okay, so this is negative 1.5. So when you sum them up, what you get is 4 minus 1.5. So you get is 2.5.